So welcome everyone to today's public global R&D. I'll be your MC today. My name is Lara, and we'll have a very nice agenda of updates, features, and demos. So I think let's take it away with Moritz, who will give us an update from the growth team.
Yeah. Hi, everyone. As already mentioned, I'm Moritz from the growth team. And today I want to highlight our latest effort to onboard new developers to build on the internet computer. And that is our Zero to Dapp educational series that we have been hosting together with Code Club. The series consists of 8 sessions hosted by DFINITY employees and also community members. And here we cover everything from the basics of the internet computer over to HTTP out calls and all the way down to the Bitcoin direct integration rabbit hole. The sessions happen twice a week, and so far we had 600 registered participants that can earn ICP by completing the weekly assignments. And our goal for the series is to be the onboarding material for developers and tech-savvy people. So Zero to Dapp acts as kind of a dry run here that we want to use to collect feedback. And once the feedback has been incorporated, we plan to polish everything, record it in our studio, and then release it on our YouTube as a go-to resource. So if you haven't signed up yet, make sure you follow the QR code on this slide to do so. There are still 3 sessions left, and all of the prior lectures have been recorded and made available on Code Club's YouTube channel. And following the educational series, we'll host a hackathon in January. So this is actually the perfect time to get ICP ready over the holidays. And this has been a cross-team effort. So I would like to express my sincere thanks to everyone involved. Without you, this wouldn't have been possible. And with that, back to you.
Thank you very much, Moritz. So we thank all of you, and we can go to the next update by Ashavir, who will tell us how SNSs are more auditable now.
So hi everyone, I'm Ashavir from the NNS team, and a very quick update on making SNSs more auditable. So as part of the recently shipped improvements for the Neurons Fund, we also were going towards making more publicly available information for the community to be able to audit participation in SNSs. And the reason why we're interested in this is because of decentralization and security. So we think that every user should ideally be able to validate their own contribution to an SNS and do so by getting information from on-chain served sources, not rely on any third party providing this information. And the main idea behind how to implement auditability features for the SNS is to be able to provide these public API endpoints, but also to provide the tooling such that every user can actually benefit from these endpoints. So here's a quick example how this can be done already for the Neurons Fund. The first DFX command here is calling the NNS governance endpoint called get Neurons Fund audit info. And if you read through the response, then you can see that it contains things such as the portion of the neuron with the corresponding amount and the hotkey principal of the controller. And this is a Neurons Fund neuron. So when a Neuron Fund participates in a SNS swap, it's expected that the Neuron Fund participant will get an SNS neuron basket, just like a direct participant if the swap succeeds. So we want to audit that this process went as expected. And of course, we need to know how many neurons are expected in the neuron basket, for which we have another endpoint on the SNS swap canister called getInit. And the third call, which we need to be able to audit in this case, is the list SNS neuron recipes endpoint that will give you a bunch of recipes, and you can then match them against the hotkey principal of the controller of your NNS neuron to see that indeed for the same controller, we have now a basket of 2 SNS neurons, and you can compare and verify that the amounts match. But all of this requires some amount of knowledge about how the canisters are implemented. So what we're going to do next is we're going to provide a plugin for DFX, such that a very simple one command is going to suffice to perform these checks for you. And this way we will enable any user of the SNS, any participant, to validate the SNS themselves. Please scan the QR code to participate in the forum discussion. That's all from me. Thanks to the other folks from the SNS team who made this possible. And with that, back to you, Lara. Thank you.
Thank you both for these updates. We can then now go to the features. And first, we'll hear from Maxims and Stefan. Maybe we'll learn about whether we can now store 100K canisters on subnets.
Hello, everyone. Thank you, Lara. My name is Maxim. I'm a software engineer at DFINITY and the execution team. And today, together with Stefan, we'll be talking about scaling the Internet Computer subnets up to 100,000 canisters. And the first thing I would like to say, it's not something we are planning to do in the future. It is already done. It's available right now. So basically, our goal for quite a while was to make our subnets to be able to accommodate up to 100,000 canisters. And why did we want to do this? Is because about a year ago, some of our subnets were growing up to the roughly 50,000 canisters in size, and they started experiencing some performance issues. And what they found out that the culprit was not the activity on the subnet, but actually the limiting factor was the total number of canisters, including the idle ones. And here we thought we can improve on that. So in order to do that, we did a bunch of profiling and improved our observability tools to be able to identify actual bottlenecks. And we did a bunch of optimizations and load testing to push the size limits of the subnets and implemented some benchmarks to prevent regressions. So let me give you a brief example of how the experience would look like a year ago for a user. Occasionally, the user might experience some long delays. Like, for example, canister call could take more than 60 seconds. And the reason for that would be checkpointing time. In case you don't know what the checkpoint is that every subnet constantly produces blocks, but every 500 blocks, or roughly every 8 minutes, it stops the execution, it stops producing the blocks for saving current state. And the longer it takes to save current state, the longer the canister on the subnet will be unresponsive. So one of our goals was to improve the checkpointing time. The second point in this list is finalization rate between checkpoints. Finalization rate is how fast the subnet produces blocks. And the subnets are aiming to produce roughly 1 block per second. And we were worrying that with the growing number of canisters, this finalization rate might gradually go down. Here, I'll talk a little bit about the optimizations in the route around executions. One important bit of work, which is not directly affecting the round execution time, but we improved a lot our observability tools that allowed us to see better the actual bottlenecks. And with a bunch of other optimizations, like minimizing the repeated lookups or improving the search of canister ID and the routing, adding additional caching for canister IDs and most popular exported functions, and improving memory management for message filtering, we were able to save about 30% of the round execution time, which helped us to secure the target finalization rate in between checkpoints. And here I would like to pass it over to Stefan. He'll talk about other optimizations. Stefan?
Hello, everybody. I'm Stefan from the message writing team. I'm going to go into a bit more detail of some other optimization we've done. So the first one I want to cover is the hashing performance. So after every block, after executing the messages, we compute a hash of the current state of the subnet. We do so, among others, to make sure that all the replicas have the same state at all times. Now, this is a quite computationally expensive step, And even more so, the complexity increases with the number of canisters because there is information about every canister in this hash to the point where it became a bottleneck. So we've tried to optimize that bit with an eye on like many canister subnets, and with a combination of parallelization and caching, we managed to get it from around 300 milliseconds to around 100 milliseconds at a 80,000 canister subnet. I'm quoting here 80,000 canisters just because at the time we rolled that optimization out, that was the largest subnet that we had. Now, this might not sound like much, a couple of milliseconds, but you have to keep in mind we have to do that every block. So we do this once per second. So over the lifetime of a subnet, this is actually a significant chunk of CPU time that we are saving. Another optimization I want to go into more detail is checkpointing performance. So as Maxim said, checkpointing is the step where we write the entire state to disk, and it leads to somewhat poor user experience as it can delay the responses to update calls. We've done quite a few optimizations to checkpointing over the last few months, but one that I wanted to highlight particularly because it's specific to many canister subnets is our optimizations for the Async step. So that's when we make sure that the data is really on disk and not in some cache. This step particularly scaled poorly with the number of files in a checkpoint, and by extension with the number of canisters. By optimizing this step, we managed to get the checkpointing time on the same 80,000 canister subnet from around 43 seconds to 22 seconds. So we saved like half of it. Now, we're not particularly happy with 22 seconds still, so it remains an ongoing focus to get this checkpointing time down even more, and that focus goes beyond the special case of many canister subnets. Another area that needed improvement was the state sync performance. So state sync is a protocol that kicks in the case where a replica falls behind for whatever reason. Then it needs to catch up, and it does so by downloading the current state from a healthy replica. Now, state sync is quite performance critical because how long state sync takes can be the difference between a replica that catches up after a couple of minutes and one that is eternally behind that cannot contribute to the consensus of the subnet. Turns out that this was another part of the code that was quite susceptible to having many small files. But by optimizing kind of for this special case, we managed to get the 5x improvement out of it from a couple of minutes to couples of tens of seconds in a typical case. So in conclusion, we can support 100,000 canisters on a subnet now, something that was definitely not true before these optimizations that we covered today. However, I would also like to say this is really just a snapshot in time. Ultimately, all dApps will want to be able to scale, and it's at least partially up to the protocol to support these ambitions. And that goes beyond number of canisters. That also means larger state, more throughput, and so on. And even beyond scalability, performance improvements are just important to get a better responsiveness and user experience at all levels of load. So there are still lots of ideas floating around in the wider community of how to improve it further. So there will definitely be future talks on more performance improvements.
Right, so I think we can go to the next presentation by Manu about ckETH.
Yes, hello everybody. I'm Manu, and I'll give indeed an update on ckETH. So I'll start by giving a quick recap of what it is and a little bit of how it works, and then share some exciting news. So let's start with what ckETH or chain key ether is. ckETH is a token that lives on the internet computer, and it will be an ICRC compatible token, so it follows the token standards that we have, which makes it easy to use in the ICP ecosystem. Like it's easy to integrate into wallets and use as a user or integrate into dApps. And as the name suggests, it's a twin to Ether on Ethereum. So more precisely, ckETH is like backed one-to-one by native ETH on Ethereum, which is held by a canister using the threshold ECDSA functionality that's available on an internet computer. So there's no like centralized single party that you need to trust for this, but the canister is holding the funds, the ETH that's backing ckETH. And similarly, this canister allows anybody to convert between the two. So you can have native ETH, and you can choose to convert it into ckETH, and then you can use it on the internet computer easily. And whoever has ckETH can ask to receive the native ETH back instead. And of course, because ckETH is on an internet computer, you can transact it fast and for very low fees, which is of course nice. And so this is very similar to ckBTC that I guess many of you are familiar with. So how will it work? One part is just the ledger canisters. So we have a ledger and an archive canister and an index canister. This is just like the ICRC canister suite. I think many of you have used this. If you use some SNS tokens, this is the setup you use. Or ckBTC use this as well. So this is kind of standard. And then we have the ckETH minter on top in the picture here. That's kind of where all the magic happens. So this canister is in the privileged role that it can mint ckETH tokens. And it does so by communicating with the Ethereum network. So it talks to, via HTTP outcalls, it talks to the Ethereum network using the standard Ethereum JSON RPC interface. And it can use that to see the gas fees or know whether it received ETH. And it can submit signed transactions using ECDSA to send ETH out to people. And so this gives it the power to, whenever it receives ETH, mint ckETH, and vice versa. Whenever people request native ETH back, it can construct such a transaction and and make it happen. So to go into a little bit more detail, suppose I'm a user that has native ETH and I want to get ckETH. What would I need to do? Well, there's actually a helper smart contract that lives on the Ethereum blockchain, which has a method that's called deposit. And in that function, you can pass a principal, which is the principal of your internet computer wallet where you want the funds to arrive. And you can make this call with ETH attached to it. So you can use this from your MetaMask, for example. You can choose how much ETH you want to attach. And now this goes to the helper smart contract. And the helper smart contract actually does very little. All it does is emit an event that this happened. So it emits an event saying, I received this much ETH for this principal. And then it forwards the Ether to an Ethereum address, which is controlled by the ckETH minter via threshold ECDSA. So what we have now is that the funds are controlled by the minter, and there is some event that was emitted. And now the ckETH minter periodically, via HTTP outcalls, contacts multiple RPC providers to ask which events the smart contract emitted. And if they all agree, it trusts that it was true. And then it mints the corresponding ckETH for that principal. So if I send 1 ETH, then I will get 1 ckETH, maybe minus some fees. And the minter can do this because it's in this privileged role of the mint that can mint tokens on the ledger. And so maybe one nice thing here for the user is that you just need to do this one call. So you just need to make this one Ethereum transaction, and the rest happens automatically. You don't need to do anything. The minter will just look for this actively on its own, and the tokens will land on your in your wallet after Ethereum finality is reached. Vice versa, I might have some ckETH I've played around with on the internet computer, but now I want to get native ETH back into my Ethereum wallet. That's a two-step process for the user. The user first does an ICRC2 approve, allowing the minter to take some ckETH out of my account. And then I call a function on the minter saying, please give me a certain amount of ETH to this Ethereum address. And you'll get some OK back. with some index that allows you to look up the status, but that's optional. So eventually the ETH should land on the requested address. Behind the scenes, there's a lot of stuff happening. The minter would, of course, burn some of your ckETH and then talk to the Ethereum network to see what the gas fees are, and use ETHDSA to sign a transaction for you, submit that transaction, periodically look at if that transaction is actually included in the blockchain or if it needs to maybe be resubmitted with higher fees. This is all stuff that the user, I guess, does not strictly need to care about. It should work without involvement of the user, but this is how it works. Then I hope you're excited about this and you want to use this. So when can you use this? DFINITY plans to submit SNS proposals to install the required canisters on Friday. So this Friday, that's December 1st. So this would be the real mainnet ckETH. Anybody can use it. There's no restrictions or so. This has been running as ck Sepolia ETH, so the testnet version, already for almost 2 months. And it recently passed an extensive internal security review in DFINITY without major findings. So in that sense, we think it's ready. Of course, it's still new code, so we should always treat it as experimental initially and rather be careful. And so this, I think, I see this as a big milestone, but it's also only the beginning, right? So we want to release this as early as possible, such that now the community can embrace it and an ecosystem can form around it. So dApps can start supporting it, maybe liquidity can start growing, but there's much more to come. So we need more nice UIs for this, especially maybe for conversions between ETH and ckETH. DFINITY is working on getting more such tokens via ckERC20, which would allow things like ckUSDC as well next year. DFINITY is also working on this EVM RPC canister that will make it easier for ICP developers to interact with the Ethereum, just with the Ethereum blockchain. So yeah, there's much more coming, but I think we're at a big milestone here. And so, as I said, this needs, I guess, the whole community to be valuable, right? So what can people do with this? Well, first, I hope that many people will actually verify SNS proposals. So we plan to submit them on Friday. So hopefully many people will take the effort to verify them, look at the source code, build the canisters, make sure it all makes sense, cast their vote, and hopefully help spread the word so that we get a lot of votes on these proposals. Developers can integrate ckETH into their dApps. Hopefully this is easy because it follows the token standards. Anybody can give this a try by converting some ETH into ckETH. And I hope to see that liquidity pools will form and people can choose to add liquidity there, can add ckETH liquidity. A cool use case that this opens up is also that people can now, in a decentralized way, trade between ICP and Bitcoin and ETH in the form of ckBTC and ckETH, which is I think a cool use case. And the ckETH minter also exposes a dashboard that explains everything it does. So it explains, okay, here there was this incoming transaction, which was a deposit. For that, we minted this ckETH, and vice versa. There was this burn, which led to this transaction. So it tries to be very transparent about everything. So anybody can, I would encourage people to look at that and follow the activity and verify for yourself that the ckETH is indeed fully backed by ETH, as I'm claiming here. And finally, there's a forum link here in the QR code. So that's where we always try to keep things up to date. So I would encourage people to ask questions here, but also there on the forum. Suggestions, feedback is very welcome. Any question we try to answer. And I think that's it from my side. So get ready to vote, and hopefully soon we have ckETH.
That's very exciting news. Thanks a lot, Manu. I think we would have time for 1 or 2 questions.
I can try to quickly look at some. So Moritz asked about this phase 2 integration. So currently this works with HTTPS outcalls, as I mentioned, to different providers, and they need to agree to make sure it's still decentralized. We've talked about plans to kind of run an Ethereum node or in some form have the full Ethereum state available on the IC itself. That's not there yet. I mean, that's still in the plans, but and then hopefully we can switch to that. But so far it's HTTP outcalls, and then later it could maybe be indeed like the management canister on the IC. Are there more questions? How long does it take? Yeah, so if you want to convert from ckETH to ETH, I think it does not take very long. I guess on the way in, you definitely need to wait for Ethereum finality, which is something like 15 minutes. On the way out, I think it might be a bit faster, but it should be overall a bit faster than Bitcoin because Ethereum has a bit quicker finality than Bitcoin.
All right. I think those were the questions in the chat. Now a new one came in. Will there be a KYT process?
Yeah, that's a good question. There will not, at this stage, what we will propose is not including a KYT process like we have for Bitcoin, but a fixed list of blocked addresses. We think that's sufficient to start, and I guess the SNS can control it after that, so things can be upgraded.
All right. So the next feature will actually be presented by me. So I want to talk about a new feature where we would like to take measures to make passing of critical SNS proposals more robust. And I will define on the next slide what I mean by critical proposals. But first, let me explain why are we working on this. So I think it all started when there were some SNSs that moved a large portion of their treasury, and sometimes with proposals that got adopted fairly quickly. And this triggered a discussion in the community on how we can prevent this in a malicious context. So say someone is able to, due to some attack or some other means, take over a lot of the voting power very quickly. How can we maybe make sure that they cannot immediately run away with the treasury, or at least take measures to make that less likely? And I think it was a very great community discussion. You can find it under the QR code linked here. So we started with a few ideas. The community members had a lot of other ideas. We also tried to make sure that all of the measures as a whole make sense together in the end. And after some days of discussion, we basically came out with 4 measures that are recommended. So first, we would like to change the following rules for critical proposals. Then we would increase the bar for voting. So we want to require a higher threshold to adopt the proposal. Then we want to limit how much tokens can be taken out of the treasury in one proposal. And finally, we want to increase the voting period for critical proposals. And I will now first introduce what I mean by critical proposals, and then present this first measure in a bit more detail and give you a summary of the other 3. So first, what are critical proposals? So together with the community, we defined that the following proposal types should be critical. You see them here on the left. First, the transfer of treasury funds. So whenever the SNS DAO moves their SNS or ICP tokens out of the treasury. Second, minting of new SNS tokens. So this is actually a proposal that does not yet exist, but is under development. And finally, deregistering Dapp canisters. So this means that if the SNS DAO owns a Dapp canister, it could give its control up and hand it to a potentially centralized party. So this last proposal type is considered critical because, of course, Dapp canisters can be very valuable by themselves, especially if they can now hold ckBTC or soon ckETH, they might hold a quite considerable value. And just to contrast this with some proposals that are now not defined to be critical, I listed some on the right. So these are, for example, motion proposals or the upgrading of SNS controlled or SNS canisters. So let's now have a closer look at this first measure. So the first measure that is proposed is to remove these critical proposals that we have just seen from the so-called catch-all topics in following. And to understand better what this means, let's remind ourselves of how following works. So this is a picture of the NNS frontend tab, and let's assume that's the view that the yellow neuron has. So the yellow neuron follows the blue neuron for motion proposals, as you can see here, and it follows the purple neuron for this catch-all topics. So what does that mean? This means that the all topics mean the all topic catch-all means that whenever the yellow neuron does not have an explicit choice for a certain topic, then the governance canister will just defer to this all topics. So maybe let's look at the detail. So you can see here that for proposals to upgrade SNS controlled canisters, the yellow neuron does not have an explicit following choice. This just means that for these types, it will follow the purple neuron. So if the purple neuron votes on such a proposal, the governance will automatically also cast the vote for the yellow proposal, for the yellow neuron. Sorry. In contrast, if the purple neuron votes on a motion proposal, that has no effect on the yellow neuron because the yellow neuron chose explicitly to just follow the blue neuron for these kinds of decisions. So this is how it works now. Let's now see what is now the proposed change for the critical proposals. So again, let's look at an example here, a treasury proposal. We just saw this is how it works now. Since the yellow neuron has no explicit choice there, we would default to the catch-all. So whenever the purple neuron votes, the yellow neuron would also vote. And now the proposal is to change that and say that for these critical proposals, we will never just use the catch-all. So in this specific case, now this means that the purple vote would not trigger the yellow neuron to vote. Note that the yellow neuron can still make an explicit choice to follow someone, but the catch-all is just not enough. And the idea here is that for these critical proposals, we should incentivize all the neurons to make an explicit decision on who they want to follow, rather than just pressing one button on this all topics. So with this, let's look at the overview of all measures. So you can see in the middle, what is the current setting for all proposals, and on the right, what would be the new setting for just the critical proposals. We have already discussed the top line. So for the thresholds, the current situation is that to pass the proposal, a proposal needs more yes than no votes, and at least 3% of the total voting power must have voted yes. And the proposal is to keep the same logic, but just increase those numbers so that newly one would require 2/3 roughly of the votes to be yes and 20% yes participation. For the treasury proposals, there is currently no limit. So the third measure proposes to introduce some limits. How many tokens can be taken out of the treasury within a given time, for example, a week. So this is really the one measure that if there is a malicious takeover, this could slow down the attacker a little, and maybe the SNS DAO could react to it in some other ways. So here the details are still being defined, and we plan to basically discuss more with the community in the coming days and weeks what exactly these numbers are here. And finally, this was also a proposal by the community that because there's now a higher voting threshold needed, we would give voters a little bit more time to vote. So now the default setting is 4 to 8 days as a voting period, and this would then be increased to 5 to 10 days. I hope this gave you a good overview. And again, you can find here the link to the forum discussion. And of course, we're happy to hear all feedback and contributions. Let me quickly look at the chat. Shouldn't SNS control canister upgrades also be critical? Otherwise, they could be upgraded to a version that tampers with the funds. Yes, that is a good point. I think we have to draw the line somewhere. I think here the main argument for the canister controlled Dapp canister, for the SNS controlled Dapp canisters is that currently some teams that are still under development might be slowed down if they need very high thresholds. But yes, one could also make the point that Frederick just made, and then maybe change them to be critical proposals going forward. Then Björn asked, are the parameters controlled by the SNS itself? So can they be changed if an SNS chooses to? No. So the answer is no. So these parameters here on the right would be set by the NNS. So this would be kind of hard-coded in the WASM. And similarly, like SNSs cannot choose their own WASM, the idea would be that they are the same for all the SNSs. So they cannot be changed. All right, then I think let's continue with the next presentation to make sure we have enough time for our demos. So let's start with Andre with the async friendly performance counter.
Yeah, hey everyone, I'm Andre from the runtime team, and today I'll be updating on the new performance counter. What is performance counter? It's a system API call. It returns the amount of work done by the canister. There is a type argument to specify what kind of counter to return. Why do we need a performance counter? We need some metric to optimize our canisters, and the more efficient the canisters are, the less cycles they pay. So it's important. For a long time, the only counter available was type 0 counter. It's the amount of work done by the current message execution. It works well, and many of us use it daily to optimize our canister code, but the counter resets after each await point, so we can do better. How? We've implemented a new performance counter type 1. It tracks the amount of work across await points. Let's compare the counters on the next slide, please. Consider this example function. The function calls and awaits 2 times before replying to the original call. From the developer's point of view, it's just one function. From the user's perspective, it's just one call. But in fact, under the hood, there are 3 message executions. At the beginning, the code is executed up until the first await point. Then a reply message triggers the second execution, and another reply message triggers the final part. This final part replies to the original call with 2 counters. To track the original call, there is a call context. The internet computer creates this call context for each call and keeps it around until the call is either replied or rejected. And now let's compare the 2 counters on the right. The performance counter type 0 just follows those 3 executions. It starts from 0 and goes up to some value I. After the first await, it resets and goes up to some value j, and then it resets again and goes up to some value k. On the other hand, the new type 1 counter lives in the call context. So it monotonically increases until the original call is replied. And in this example, it goes from 0 to I, then to I plus j, and then up to I plus j plus k. The result seems to be quite similar, right? So why can't we just use the old counter? Why do we need this new one? And on the next slide, please, it will be clear. To get the same result, I plus j plus k, using just the counter type 0, we need to save the counter before it resets. And even this simple example becomes some sort of spaghetti, as we have to touch every single await point. You can imagine a bit more complicated code with many nested functions, library calls. It's really a challenge to properly instrument production async code with this type 0 counter. On the other hand, this new call context counter, we still need to explicitly get the counter at the end, but now we don't need to change any nested function or libraries. We just need to do it once at the very end. So it's a huge step forward to fully automate the instrumentation at some point in the future, I believe. And I think we're really close to that goal now. yeah, on the next slide, there is a, okay. So this is the DFINITY example repo. There is a new performance counter example there. Let's quickly glance through the code. So at the beginning, there are some comments, there are some helper functions. Yeah, so here is a very interesting example of the nested update calls. It prints a lot of details on the console. Here is another really interesting example for the nested query calls. It also prints a lot of details. Please check it out offline if you are interested. But we will focus on these small example functions we've seen on the slides previously. So basically, it's what we've seen on the slides. It's a function which does some work, awaits for the call, does more work, awaits for the call, and at the end, it just returns performance counter type 0 and performance counter type 1. Let's try to run it. There is a command we can just copy paste. Okay, so the call returns two values. The first one is the old type 0 counter, and the second one is the new type 1 counter. As we can see, this new counter reports much more instructions, 21 million versus just 7 million. Just because, like we saw previously, this new counter, it includes all three executions. And basically, this type 0 counter, it gets resets after each await points. So basically, it reports just the final execution. Yeah, and that's basically concludes my demo. If we could go to the last slide, please. Yeah, just quickly on the last slide. So basically, this new call context performance counter, it's available everywhere. The example is on the GitHub. Please check it out. And as always, many thanks to everyone involved. Thanks a lot, folks. We did it together.
Thanks a lot for this presentation. I think we don't have a lot of time left, so I would propose to take the questions on the chat, and then we can maybe go to Andrew for the next presentation. I think you want to share your screen, right?
Yes, thank you. Hello, everyone. My name is Andrew, and these days I've been helping the Geeks team with some product management tasks. I'm mostly focusing on the NNS front-end app. If you were on the NNS front-end app in the last few days, you may have seen there is a new button that's called Buy ICP. And today I would like to focus or spend a few minutes on walking you through the flow of how this button works and the motivation behind it. And the motivation to introduce this button was to make it as simple as possible for first-time new users or new users who may not have ICP right away to start experimenting with the NNS app and with the governance of their computer. I have a video that I prepared because unfortunately I can't give a live demo because this whole user flow requires a lot of personal information that I would have to put in that I would rather not share publicly. So once you click this button, this brings up a modal window that has now just one button, that Buy ICP with Banksa with a little disclaimer. And later on, we are planning to add more fiat on-ramp providers besides Banksa so that users can have more choices, but also to cover more countries and then and more fiat currencies. And once you click this Banksa button, while this still has the same coloring, this takes you to the Banksa website that outside of the NNS, and it automatically fills in your wallet address. So it's now currently blacked out, but if you go through it yourself, you will have your wallet address automatically filled in, which is very useful for first-time users, that they don't have to be afraid that they might have the incorrect wallet address that they would send ICP to. And I think from this point, it's a pretty normal KYC process. If you've been through it before, you have to do an email verification, and once the email verification is done, then you're asked to provide some personal information like name, address, and then go through the KYC process. And then when the first time I went through this flow, it took me about 10 minutes end to end. Of course, I also had an image of the back and front of my ID handy on the computer. Otherwise, but yeah, even with the way now this video is a bit cut short so that it doesn't take this whole 10 minutes. Otherwise, it's relatively simple and quick flow. And this is me in the Zurich office doing the KYC. And once the KYC is done, I managed to do it on the first attempt, so there was no issue on the KYC side. Once the KYC is done, then you're shown a payment system, and this is now just a regular online purchase. Once the payment is successful, then you have this loading screen, and now the video is sped up. But what happens is it takes a couple of minutes while the payment goes through, and also while the ICP goes to your address. So in here, when I did it a couple of days ago, I had to wait a couple, like 5 minutes before the ICP landed on my NNS account. Once you go back to the NNS and refresh, then you should see the ICP already in your account. And that is pretty much it. One thing to know that if you already have ICP, or if you're using Coinbase, Kraken, or Binance, or any other exchange, then it's probably best to keep using them, because banks and most likely other fiat on-ramp providers will charge higher fees than regular exchanges. And a big thank you to Artem and Lorenz for the design and the implementation of this feature. I think that's all I have to say.
Thank you very much.
So hello everyone, I'm Luca, and today I'm gonna present you IC WebSockets. As some of you may remember, a few months ago, Jakub Sliwinski from the DFINITY team published a proof of concept that he also presented in one of these R&D calls. And from there, we started a few months later, we started with our implementation, and we are still collaborating with Jakub on the IC WebSocket protocol. Let's see why you need WebSockets. Let's say your canister at some point wants to send an update to the front-end application that you are developing. The problem is that the canister cannot do it directly. So what you have to do is that your application from the front end would need to keep polling in order to get new updates, new messages, or whatever from the canister. And this could be a problem, because this means that every client would need to poll the canister, and it can become a problem if and when the IC will start charging for query calls. How can we solve this? In a normal Web 2 application, what you would do is that you would open a WebSocket connection with your server, and then the server can decide when to send messages to your frontend. But of course, here we have a problem, because how can we open a WebSocket connection to a distributed system from the front end of our application? For this reason, we developed the WebSocket gateway, which you can think of about a bit of the equivalent of the HTTP gateway that is already available. And what the WebSocket gateway does is that from one side, it exposes a WebSocket interface to which the application can connect. And on the other side, it takes care of polling your canisters from the IC. Of course, this reduces the number of pollers because now only the gateway is the one that polls the canister, while all your clients or all your front-end clients can be connected to the gateway. But this introduces a problem. So the gateway is a single point of failure, and it could also act maliciously. So we need to detect when it does. And to do that, we implemented some measures in the protocol that help us detect if a gateway acts maliciously, or also if a gateway is not working at all. But we went further, and we enabled the protocol to we enabled the protocol so that a front-end application can connect to many different gateways, even dynamically at runtime. and the gateways poll the canister and can still give you the messages that the canister have to send you. So you can switch from one gateway to the other without caring about who is hosting it. Okay, now that we have seen why we need WebSockets, let's see how we can integrate it in our Dapp. And let's start from the front end. For those of you who are familiar with the traditional WebSocket API available in the browser, you will also be familiar with our library, which is the IC WebSocket.js, because as you can see here, you can first give the server to which you want to connect to, in this case, the gateway that we are providing at this URL, then some other parameters that you may need, and then of course you need, which is the difference between the traditional WebSocket API, is that you need to define, to give the library some additional parameters that are IC specific. And as you can imagine, you have to communicate to the library the canister to which you want to connect to, the network, the IC network to which you want to connect to, and you also have to pass an identity here. And we'll see later why you need to pass an identity. And there are some other parameters that are not relevant here. And then you can move on and define your business logic. So you can define the callbacks to the events that happen. And as you are familiar with the traditional WebSocket API, you will find these methods familiar. So when a connection is opened, you want to react in your application. When you receive a message, you want to do something. And the same for when the connection is closed or if there is an error from the WebSocket. And finally, from your code, at some point, you want also maybe to send a message through WebSocket directly to your canister. And you can do it by calling simply the method as you would do in a traditional WebSocket implementation, just ws.send and the content of the message that you want to send. Let's go on the canister and see what we have to do to integrate WebSockets. We will show you the Rust example, but the Motoko library is also available, and I will show later other libraries available. So you have to install our IC WebSocket CDK, and then you can define your business logic again in the callbacks. So you will be notified when a client opens a connection with the canister, when you receive a message from the canister, and also when a client closes the connection. Then you pass these callbacks to the parameters of the IC WebSocket, and finally you can call the init function that makes you initialize the CDK. Then, of course, we are on the canister side, so we need to expose some methods that make the canister IC WebSocket compatible, let's say. So the protocol needs some method to interact with the canister. And as you may expect, these methods are pretty straightforward. So you have to define 3 update endpoints, which are the WS open, WS close, and WS message. And inside, you can just use the methods that the CDK provides without doing any other logic in it. And then there is another method, which is the most important one, and it's the WS get messages, which is the method that the gateway keeps polling on your canister when you open a connection, a WebSocket connection. And as you can see, it's a query method, of course. And then at some point, again, you want to send a message to your client. And what you can do is that you simply use the WS send method from the CDK, and you specify the principal to which you want to send the message and the content of your message. So the libraries available are the Rust CDK, the Motoko CDK, and the JavaScript SDK. Then the community already started working on it, and there is already a Java SDK available to use. So from the front-end side to interact with the canister. And then there are 2 other SDKs coming, one for Golang and then one for C#. And the last one is particularly interesting for the games that are developed on the IC. Let's have a brief look at what's behind the IC WebSocket protocol. So I told you that we have implemented a way to detect if the gateway is cheating or if the gateway is acting maliciously. And the attacks that the gateway can do are tampering the messages, so changing the content of the messages, reordering them and sending them in a different order to break your application in some ways. It can block completely the messages and not relying them to you, and it can also read the content of the messages. So in order to avoid the gateway tampering the messages, we implemented signatures, and that's why you need from the client to specify an identity, because the identity needs to sign the messages that arrive to the canister. And then on the canister, we are using the certified variables to certify the messages.
Luca, we're slowly running out of time. If you
yes,
can
sure.
go through the rest,
other attacks can be the sequence. The reordering of the messages. We have sequence number in the messages. Then we have acknowledgements. So both sides, frontend and backend, can acknowledge messages on themselves. And then when we'll have vet keys, we will also be able to encrypt the content of the messages. My question now to you is, how will you use WebSockets and how you will implement them in your application? To help you, we have a tutorial to get started, and then you can also join our Discord community, in which we published other examples, like a chat example, or also with Motoko CDK. And then a little super quick demo, which is available at demo.icwest.io. So basically, it's a ping pong demo. So let me restart it now. And what it does is that it opens a connection with the canister, and then the canister first sends a message, as you can see here, to the front end, which then replies to the canister, which then replies to the front end, and so on. So it keeps going like this. That's all. We hope you to support you in implementing WebSockets in your application, and thanks a lot for this opportunity.
Well, then I also thank everyone for joining, and thanks a lot, Luca, for this interesting demo. Yeah, and thanks everyone for joining. I think that was it for today. I wish everyone a great rest of the day.